Hi guys, it's Kate. This is my second video on optimization, and my goal is to try to put some of the tips and techniques and structure that we talked about in the first video into practice with two different optimization problems that come off of the worksheet from the first class on optimization. As a quick reminder, we'll be talking about how to identify when a question is an optimization question. We'll be honing in on these keywords here: largest, smallest, greatest, least, etc. Then we'll be using a consistent structure to analyze these problems. We're going to be building a function that models the quantity we want to maximize or minimize. Then we'll be analyzing that function to identify the desired max or min, and then we're going to take a moment at the end to answer the original question, because frequently it's not just what is the maximum value or what is the minimum value. It's something about the physical properties of maybe a box or a picture frame or a window, whatever it is, that occur when a particular value is maximized. In this video, we're going to be engaging in consistent application of the strategies that I discussed in the first video. I'll be cueing you and encouraging you to pause the video to read and reread the problem at different points, looking and filtering for different types of information throughout. I'm going to be asking you to write down in clear, complete sentences as part of your answer what your objectives are at particular stages. And then I'll also be cueing you to connect the mathematical notation that you're writing down on your paper to the real-world example of the problem you're discussing. And by applying these three tips consistently, I hope to have an approachable but flexible framework that you can apply to any optimization problem that you encounter on a homework assignment or an examination. Having a consistent but thorough and flexible problem-solving strategy in place can really help you feel less stressed out about these problems. So let's get started. This is problem 4 from the first day on optimization's in-class worksheet. I'd like you to pause the video and read through it. And if you are going to encounter this problem in the wild, so to speak, sort of on an exam, what would cue you in your reading through that would help you identify that this was an optimization problem? Go ahead, pause, read, and we'll discuss that in just a moment. Did you catch it? There's a lot of information in this problem, as there's a lot of information in many optimization problems, but it's in that last sentence where it says if the track around the fountain is going to be 440 yards long, what dimensions would maximize the area for the fountain? That keyword, maximizing the area, tells you that this is going to be an optimization problem. Now, you may be able to say at this moment, but if not, take a second rereading of the problem, and I want you to filter for enough information for you to sketch an example of what's going on and to state your goal. What physical quantity are you trying to maximize or minimize? Just saying, I want to maximize or minimize, and put a word there, not anything mathematical yet. All right, let's take a look. In this problem, a park is being constructed and there's this beautiful fountain that people want to install in the park. We read as we move sequentially through the problem that the fountain will be in the shape of a rectangle, which I'm going to sketch here. Then it says there's going to be a walking path in the park to enjoy the fountain. The path will follow two opposite sides of the fountain. So for instance, those two pieces could be the walking path, and then it says, and two semicircles on the other sides of the rectangle. So we have a reasonable working sketch from our reading, and then as we move to the very end, it says, if the track around the fountain is going to be 440 yards long, that's not for my sketch. It says, what dimensions would maximize the area for the fountain? Now, the other thing that we wanted to be able to do from this rereading is to write down our goal, which is what are we trying to maximize or minimize? And it tells us right here, we are maximizing the area for the fountain. So I'm going to write that down explicitly. And it's those two pieces that will be really, really important. We want to maximize the area of the fountain. I have a good sketch working. Now, in our next step, we're stepping now into part 1 of our problem-solving strategy, which is to create a function that models the quantity we're trying to maximize or minimize. So we want a function that will give us the area of the fountain. And as we saw in the previous video, this doesn't have to be a very sophisticated function at first. We're just going to write down the basics of what we know. We know that the fountain is rectangular. And so in order for us to find the area of the fountain, the area of a rectangle is going to be length times width. Let's write that down now. And since we've introduced variables into this via our area equation, I want to now label that length and width on my picture as well. So let's do that. So we have our function, but unfortunately our function is a function of two variables and not a function of one variable. We need to get it there because our optimization skills, our ability to locate and classify critical points, only works with functions of one variable. So right now I want you to reread the prompt a third time, filtering for additional information that we have not yet used that would create a mathematical statement of how the variables L and W must relate to each other. Take a moment, pause the video, go ahead and do that. Did you find it? The one clause that we haven't quite used yet is this one. If the track around the fountain is going to be 440 yards, it's that one right there. That's the last thing that we haven't used. We've used everything else, but it's that piece that will provide this relationship between W and L. This is called our constraint. I'm going to highlight it in red, and then I'm going to color code it down here and do work with the constraint in red as well. Now, why is it called the constraint? Well, it's called the constraint because it gives us information that says, hey, W and L can't be whatever we want. It's saying that if you choose W and L, it has to be so that this length, the track around the fountain, is going to be 440 yards. Okay, so let's say that 440, how do we take this, if the track around the fountain is going to be 440 yards long, statement, and put it into a mathematical equation? Well, it means that 440 is going to be this length and this length and this length and this length all added together. So the more straightforward part is the 2L lengths. Let's put those in. The next part has some subtlety to it. We have two semicircles, one on one side, one on the other. Together they do make a complete circle, this length and this length, even though my art doesn't necessarily indicate that would be the case. But we know that's going to be the total circumference of a circle. And circumference, right, can be written as either 2 pi r or pi d. I'm going to write that very faintly in gray, where d is the diameter and r is the radius. And we want to be using, we don't want to be introducing more variables. We want to be using our length and our width within this context. And so we need to notice that width is the diameter, or width is equal to 2 times the radius of that semicircle over there. And so when we're looking at this circumference expression, which would give us the length of this piece of the track and this piece of the track summed together, we find that it's equal to pi times the diameter, which is the same thing as pi times width. So we want to add that in right here. This constraint allows us to write L or W in terms of the other variable and take that statement and update our area function with that, so we can transform our area function, which is currently a function of two variables, into a function of just one variable. Now, as I discussed in the previous problem, you can check the constraint to say, which would be easier to solve for in this statement? Or the area function, which would be easier to plug in for in this statement? In this particular problem, there is not a huge difference. You're going to be doing the same amount of work in either direction algebraically, and so you can pick. What I'm going to do is I'm going to pick to solve for, let's say length. I don't know, you can pick W if you want. And so I'll solve for length over here. Let's do that. Put the video on pause and go ahead and compute that. So we have this constraint rewritten as a statement about what L equals in terms of W. We're going to take that and we're going to now update this area function so that it reflects this constraint information, meaning we're going to take this restatement of L with this constraint condition and plug it in right here. And we'll have our area function in terms of one variable. Before we move on to step 2, we do need to figure out what the domain of this function is that's relevant to our problem. Now remember, the domain is what values can W take on? What are the allowable inputs here? Now if you encountered this function outside of the context of this problem and didn't know that W had some real world significance, just looking at this, you're like, oh, well, W could be anything. W could be negative, it could be 0, it could be positive, right? If you looked at this function, just found it on a worksheet or something, it had this wasn't even an area function, it was just like 440 minus pi times W over 2 times W. What is W allowed to be? It could be any real number. But in this problem, W specifically means the width of this fountain. And if you're thinking to yourself, okay, W means the width of this fountain, now that you've added that additional significance to W, what value or values can W take on now? Well, a negative width measurement makes no sense, so W cannot be negative. And if W were 0, this fountain would cease to exist. So W definitely cannot be negative or 0. The very smallest that W could be would be 0, non-inclusive of the endpoint. So any positive number greater than 0. So we're going to say the domain here is going to begin at 0, but I'm not going to include the endpoint. What's rather interesting about that is if you did a small sketch of what the fountain would look like if W is very, very small, close to 0, but not exactly 0, you would have this comical fountain situation. Let me do a quick sketch of it over here. What's happening in an instance like this, and this is clearly from very high up bird's eye view, is that this track, the 440 yards long of the track, as W gets really small, these two semicircular sides shrink to almost nothing. And the 440 yards is really being spent by this 2L piece on either side. And W and L have that very interesting relationship that you come to see in a lot of optimization problems, which is that they are in competition with each other. If W gets very, very small, L is reaching towards the largest that it can be. And this constraint is exactly what demonstrates that. Note that if W gets really, really tiny, this term is contributing absolutely nothing or close to nothing, right? And the 2L is really what needs to hit that 440 for the total length of the path around the fountain. And vice versa, when we're looking for the upper bound of the domain, we want to think about the opposite happening. What if length were contributing almost nothing and it fell to width to do that instead? What would that look like? I'm going to do a quick sketch of it here. So if L is close to 0, width is really taking over here, and that means that that 440 foot long path is really being spent on the two semicircular pieces. Similarly, L itself cannot be 0, just like W cannot be 0, because then the fountain would cease to exist. But in order for us to find this upper bound here, what we're really looking for, it's not going to be inclusive, just like the lower bound was not inclusive. But we're looking for the scenario where L is 0. What would W have to be? So we can look back at this constraint and say, hey, if L is 0, that's where W is going to be maximized. The burden is really on W to spend that 440 feet of walking path. And so I can do a quick calculation on the side here that will tell me what would W need to be in order to spend all of the fencing on the semicircular sides. And so I found that the absolute most, if we were just spending the path on the semicircular sides and L is very close to 0, that W would be approaching 440 over pi. Again, not achieved on that endpoint. So we've created our function in one variable and the domain. And now we move on to stage 2. Analyzing this function, we're trying to find its maximum. The first thing I'm going to do is I'm going to take a step before I take the derivative and set it equal to 0 in order to find critical points. To note that we have no critical points from the endpoints of the domain because they're not included. And I'm also going to rewrite this algebraically so that taking the derivative is a bit easier. I'm going to lay out my work similarly in each of these problems. On this side, I'm going to take the derivative, set it equal to 0, and find the critical point. Here, I'm going to test the critical point, and here, I'm going to go back and answer the final question. You'll see me do this again and again and again. All right, let's first algebraically rewrite this. I'm going to put each of these terms in the numerator over 2 and then also distribute this w to both terms. So let's do that. All right, now in our next step, we're going to take the derivative and set it equal to 0, then solve for w to find any values for w where the derivative is equal to 0. Those are our critical points. Go ahead, press pause, and take a crack at that. We found a critical point. We need to make sure that it's inside our domain. In this case, 220 over pi. Is it within 0 and 440 over pi? It sure is. It's a positive number that's definitely less than 440 over pi. So we have a critical point here, a valid critical point within the domain that we're looking at. We now want to test that this critical point is actually a maximum. There are two options for us. We can either take a look at the first derivative here and see what happens if w becomes greater than 220, in which case, note that at 220 over pi, these two terms are exactly balanced. If you increase w's size, this term becomes larger, and the whole thing will be negative, meaning the function will be decreasing beyond 220 over pi. If it's a little bit less than 220 over pi, this term will be larger, and this whole thing is positive, which means that for values less than 220 over pi, the function is increasing. So you could do a first derivative test and say, oh, it goes from increasing to decreasing, so that's definitely a max. Or I really prefer the second derivative test here just because of how easy it would be to take the derivative of this function. So I'm going to do that here in the middle. We find that the second derivative is negative for any value of w, which means that it's concave down. The whole function is concave down. And this makes sense, right? If it's possible to make sure that this confirms your understanding of how the function behaves. Here we had a quadratic function. There's a negative coefficient on the squared term, which means it's a downward facing or downward opening parabola. So you would expect that concavity over the entire form. So this confirms what we already know. If it's possible to visualize that original function, make sure that the first derivative and the second derivative make sense given the original function you came from. This is not always an option, but when it is an option, take it. So we see here that this is a negative second derivative, meaning that it's concave down, and therefore we're at a max, and we want to write that explicitly on our piece of paper for our grader or for our own sanity, both of them really. Excellent. We have finished stage 2 of our problem-solving process, and stage 3 is to go back and make sure that we are answering the question completely. So we go back to the final sentence that said if the track around the fountain is going to be 440 yards long, what dimensions would maximize the area for the fountain? Now I just need to take this width value that I know happens at the maximum and figure out what the length value would be. And so let's do that. I want to plug that 220 over pi is definitely going to be my width dimension, and I want to plug 220 over pi right in here to figure out what our length would be. Pause the video, go ahead and give that a try. And we find that length is 110 yards, width is that 220 over pi yards, and that is our final answer, and we're done. Take a moment and appreciate how we used multiple readings of the problem throughout to filter for important pieces of information depending on which stage of the problem-solving process we were at. We started with an idea of what our goal was, trying to get a realistic sketch on the paper. Then, once we figured out what we wanted to maximize or minimize, beginning with a function of multiple variables, rereading for constraint information, meaning length and width cannot be whatever we want, then incorporating the constraint information into the function of multiple variables, in order to get a function of one variable, which we then analyzed. We made sure that we were able to confirm a maximum occurred at the one critical point we found, and then we were able to go back and answer the original question. Let's do one more example. Oh, and also please always circle your answers. We're going to apply the same process in this problem. So take a moment, pause this video, read the problem through, and hone in on the phrase or phrases that if you weren't watching the optimization video would tell you, hey, this is an optimization question. All right, go ahead. Did you catch it? Yes, there's this whole discussion of how Walter wants to make this jewelry box and the expense and rates of how much the wood costs for the sides and for the bottom and the top. And then it says that he wants to get a box with the largest volume possible. And that's the moment right there. Wants to get a box with the largest volume possible. That's what's telling me this is an optimization problem. All right, now I want you to pause, right? Pause this video. We're rereading again so that you can do two things. You can create a sketch, and then you can write down your goal. I want to maximize or minimize, and then a word that follows. Go ahead. All right, let's go ahead and make this sketch. He is planning to buy a custom-made jewelry box for his mom's next birthday. Great. The box will have a square base. All right, we're drawing a box with a square base. Let's do it. All right, I drew a box with a square base. I'm going to get to labeling with variables, which you may have already done, but I also wanted to write down what the goal was. Now, I know there was this whole sentence that talks about how expensive each of the sides will be, but that's not something I can really incorporate in my drawing. So remember that this reading was just to draw a sketch and write down our goal. Our goal here is that he wants to get a box with the largest volume possible. So I'm going to write down that we want to maximize volume. And it's that physical quantity, volume, that is going to be the function that we want to build. Now, a box, volume of a rectangular prism, is going to be length times width times height. But in this particular case, note that length and width, the bottom of the box, right, these pieces, right, here and here, are going to be the same because we're told it's a square base. So I'm going to write down a general formula for volume. Then I'm going to update this with the fact that it's square. I've done my best to sort of communicate that with the pictures, that instead of calling one side of the base length and one side of the base width, I'm just going to call them both S. You could definitely have just called them both L or just called them both W or whatever letter you want them to be, but the important thing is that somehow you've mathematically reflected that they are the same. And so what we have here is that volume is now going to be S squared times H. And we have S and H labeled in our drawing. Now, here we go, third reading. I want you to go through this and figure out what is the constraint. What tells us that like S can't be whatever we want it to be, that this box can't be as large as we want, that this box can't be as tall as we want. What is it that's keeping this box to be a particular size or set of possible sizes? Read through the prompt, highlight the sentence that's telling you that, and try to write down the sentence or sentences that are relaying that information in mathematical notation. Go ahead. Do you think you have it? You're absolutely right. If you're looking at the sentences we simply haven't used yet. What those are all these sentences that are telling us the cost of each type of wood and then the amount of money that Walter has to spend. So it's really this piece. Walter has $60 to spend on the present. And then these pieces up here, the sides and bottom will be made out of mahogany, which costs 30 cents per square inch. The top will be made out of maple, which costs 50 cents per square inch. but it's really this piece right here that Walter has $60 to spend on the present. So that means the total cost of every single piece, each side, the top and the bottom, has to sum to 60 bucks. All right, let's take a look at how to write that down mathematically. So this means that the cost of the bottom, the sides, and the top has to sum to 60 bucks. Well, in order to compute the cost of one of the sides, we're looking at these rates up here in this summary of the problem. 50 cents per square inch, 30 cents per square inch. Those are all per square inch. Square inch, that's a surface area unit. And so we want to take the area of these sides, which will be in square inches, and multiply it by this price, which will be 50 cents per square inch or 30 cents per square inch, and we will end up with the total cost of each of the pieces of this box. Because we'll be taking some cents per square inch and then multiplying by square inches. Now, because we started with dollars right here, $60, I want to convert these 50 cents per square inch into a dollars amount. So you'll see $0.3 per square inch or $0.5 per square inch. Let's start with the bottom. The sides and bottom are the mahogany pieces. The bottom here has a price value of 30 cents per square inch and an area of S squared here because it is a square bottom. Let's keep going. We now want to look at the sides. They're still mahogany, still 30 cents per square inch or $0.3 per square inch. The area of each of the sides is actually the same because one side is always S along this bottom face, and then we also have H. So this is S times H, this is S times H, this is S times H, this is S times H. We have 4 of them. So we want to take that 30 cents and multiply it by 4 times S times H. And last, we have the top, that is the expensive maple. The top is a square as well. Its area is the same as the bottom, which is S squared, but instead of multiplying that by the price of 30 cents per square inch, we have 50 cents per square inch. So we have 0.5 times S squared. That's our constraint. I'm going to take a moment and simplify it a little bit because we have similar terms here and here. I also took the liberty to actually multiply 0.3 by 4. Okay, so now we have this moment where we have our constraint here in red and we want to solve for either S or H, and we can take a look at which one would be algebraically easier to solve for out of that statement, or which one would be algebraically easier to plug into in this statement. And in both cases, wow, there are so many S's here, do not want to deal with that. So I would much rather solve for H here. And when I look over here, I'm like, oh yeah, I wouldn't have to square anything if I plugged in for H. So we are going to solve for H over here and then plug it back into the volume to update our volume function, move it from a function of 2 variables, which are S and H, into a function of 1 variable, which will just be S because we'll have learned how to express H in terms of S. Let's do that. Go ahead, pause, and give that a shot. All right, here's what this looks like. I took my constraint, solved for H, then plugged that back in for H over here into our original volume function. So I'm updating the function we're trying to maximize with the information from the constraint. I took an opportunity to divide out one of the factors of S here, so now I have this. And we want to take a moment before we go into the analysis of this to determine domain. Now, as I said in the previous video and in the previous problem, if you just encountered this function and were told what could S possibly take on, what are the appropriate values, allowable values for the input, and you had no idea that this function actually was talking about a jewelry box, you would look at this and be like, oh, you know, S could be anything. It could be negative, 0, positive, etc. But of course, when you start to give more specificity to what this model is attempting to compute, no, S, the side length of the bottom, cannot be absolutely anything. Cannot be negative, that makes no sense. It also can't be 0, the box would fail to exist. So S will be greater than 0. And we can take a look at this constraint right here. I like this one the most, which tells you how S and H are related in order for this right-hand side to always equal 60. Now, if S were 0, which means that the base is almost nothing. It's shrinking, shrinking, shrinking. In order to spend $60, this box would have to become extraordinarily tall, right? You would have to spend the $60 on these 4 sides. And it would be a really tall box because if the bottom and top are shrinking down, right, that means the expensive piece is not at all costing very much because it's just so tiny. And also the sides of this, it could be really tall, but this is going to be such a short amount. You could imagine this becoming comically tall. So as S gets close to 0, it's really H. The burden lies on H in order for this to equal 60. And vice versa, when S is very, very large at its sort of maximum, quote unquote, whatever that may be, that's definitely going to be happening as you start shrinking this height down, right? If you shrink the height down, that means that the burden is now on the bottom and the top in order to spend down the $60. So it's interesting. There's like these 2 extremes. There are these really tall, skinny, narrow boxes that would look something like this. Comical jewelry box, right? That's what happens when S gets really small. It becomes up to the sides rather than the top and bottom to spend the $60. But on the other hand, right, if the height decreases, that means that the top and bottom now need to take over the onus of spending the $60 because the sides will not be much at all. And a box like that would look something like this. I mean, either of these would just be ridiculous to try to fit anything in, but I'll take it. In order to compute what the upper bound would be, we're looking at a scenario where H is going towards 0. Of course, if H is actually equal to 0, the box fails to exist, so this will not be an achievable maximum for S. But we can calculate what S would be by plugging in 0 for H into this right here. And so again, this is not an achievable upper bound because this box wouldn't exist if height were 0, but there is this tension between S and H. If S is really, really, really big, it's up to H in order to say, whoa, whoa, whoa. Let's shrink this back down. If S is really, really small, it's up to H in order to swell in order to hit this $60 to spend on the gift. So in order to find this, we've plugged in 0 for H and solved for S. It's the square root of 75. 0 for H is not a box that exists, so we're not going to include that endpoint, but that is where the upper bound is. Now we have the function, we have the domain. We now want to analyze it by taking the first derivative and setting it equal to 0. Now, one thing that you can do is first algebraically simplify this before taking the derivative, and I'm going to do that in a couple of lines. I'm going to both take 60 and 0.8 and put them over 1.2 and also distribute this S. One thing I really like when dealing with decimals is to convert them into fractions. So it's really helpful for me to express 1.2 as 6/5. 60 over 6/5. You have that 5 come up, that becomes 300 divided by 6, which is 50. So I have 50S from that S distributing. And then 0.8 is 4/5, 1.2 is 6/5. That's also 4 over 6, or 2/3. And I have that S squared, which gets multiplied by S, so I have S cubed. This is much easier for me to take the derivative of. So let's do that. Put the video on pause, give it a try. I have 50 minus 2S squared. I'm going to set that equal to 0 and then solve for S to find some critical points. If you set it equal to 0 and solve, you'll get that S could be plus or minus 5 in order for the derivative to be equal to 0, but note that our domain only involves positive values of S between 0 and square root of 75, so positive 5 is the only critical point that comes out of this because negative 5 is outside of the domain of our function. Now, put this on pause and try to analyze this. Do you want to use the first derivative test? Do you want to use the second derivative test? See what you come up with. Confirm that this is a maximum. All right, here's what I did. I erred to the second derivative test side of things. You could definitely have done the first derivative test. It just seemed like a more straightforward second derivative to take. My second derivative was negative 4s. When I plugged in s equals 5, I got negative 20. So my second derivative is negative, so that means that the function is concave down there, and I am at a maximum. And then our last step is to make sure that we are actually answering the question. Going back, what was the original question? Oh dear, look at that. It says, what dimensions should his box be? Okay, well, we have S, right? We have one of them from our work so far. That's the S equals 5 piece of it. That's where the maximum's happening. We just need to figure out what the H is there. And so we can go back to this moment with the constraint and say, oh, let's plug in 5 for S and figure out what H would need to be there. Pause the video, go ahead and calculate what H is when S is 5. I found that if I plugged in 5 for S, I would get that H was 20/3. So in order to format my answer really nicely, I'm going to say my final answer, the dimensions for this box, are 5 by 5 by 20/3 inches. The end. If you have any questions, please don't hesitate to ask. I'm hoping to upload one more video on applying this problem-solving process with the rereading techniques as well as sort of spacing and laying out the work similarly. Note that in this particular problem, we had a desire to maximize volume from largest volume possible. That gave us the foundation to begin working on a function that would describe volume here. Our constraint was how much money we had. That's what meant our box couldn't be however big we wanted it to be. We only had $60. And so 60 allowed us to describe one dimension of the box in terms of the other, which updated our function of 2 variables into a function of 1 variable. By thinking through what the various extremes would be, we got our domain in place. And then we were able to apply the first derivative analysis to find a critical point within that domain and then test whether that critical point corresponded to a maximum, and then finally answer the original question. I hope you found these videos helpful. Remember to go about your work consistently. It's really the consistency within your practice of thinking through these problems similarly, of trying to isolate the information in the same way every time, that will get you to a place where you're really confident and actually looking forward to tackling these types of problems on an examination. If you have any questions or concerns, please don't hesitate to leave a comment in the comment box below on this video. Have a great one.